Okay, so for this example, there's so f of x is 1 over tangent, the derivative is this. Before I even do part b, because it's a and b, I am pretty sure that I am going to have to use this relationship somewhere in my problem for part b. So if I'm going to do this, so the first thing I'm going to do is I'm going to rewrite this as tangent x to the minus 1. And so now when I start to do the derivative, I'm going to pull the minus 1 down, and it's tangent x to the minus 2 times the derivative of tangent x, this is the chain rule, is going to be cosine squared x. So if I simplify that, that's negative, because it's negative 2, it's on the bottom. Oh, hold on. The derivative of tangent x is not cosine, it's 1 over cosine squared x. So what I have now is I have 1 over tangent squared goes on the bottom. So this is tangent squared times cosine squared. Well, tangent I know is sine over cosine. I can square them both since it's tangent squared times cosine squared x. Those cancel and ta-da! I get 1 over sine squared x, which is what I was hoping for. All right, so now in doing b part, what I'm going to do is I have an airplane. Here's an airplane. It's flying. Here's the flight path of the airplane. And the airplane is here. It is 2,000 meters high. And so the observer is watching the ground directly beneath the flight path and measures the angle of elevation of the plane at 0.5 radians. So if here's the ground, here's the flight path of the plane, here is the observer O, observer, he sees the airplane. The angle of elevation goes up, so here is the angle of elevation, theta. And so it's 0.5 radians, and the rate of change of this angle is 0.01. Find how fast the plane is traveling. Well, I'm looking for, if this angle is positive, that means it's getting bigger. It means this plane is flying in this direction here. And so here is this is 2,000. By symmetry, I know this is also theta. And so if I call x, and this is a fixed value of 2,000, I know that d theta dt is equal to 0.01 radians per second. And I'm asked to find, if this is the path of the plane, I want to find how fast it's going. That means I want to find dx dt. I want to find dx dt when theta, beneath the path measures the angle of elevation to the plane is 0. So right, when theta is equal to 0.5. So I need to find a relationship between x and theta and 2,000. Well, I'm feeling like for some reason I'm going to need this scenario here. So if I know that tangent theta is equal to opposite 2,000 over hypotenuse, so not hypotenuse, adjacent, and so I need to find, if I rewrite this, x is equal to 2,000 over tangent theta. And here we go. We want to find dx dt. I can find, well, dx dt is going to equal to dx d theta, because this is x in terms of theta, times d theta dt. So I know that dx d theta is going to be 2,000 times, this is 1 over tangent, so the 2,000 is just going to be carried forward, so it's going to be minus 1 over 2,000 times 1 over sine squared x. is what we were just shown here. And that's dx d theta, because I did all my calculus work in the blue here to find the derivative. So now I want dx dt. I know that it's negative 2,000 over sine squared, and this is, here I is x, but right now it should be theta, so theta times d theta dt, which is 0.01, 0.01, and I'm going to do this when theta is equal to 0.5, 0.5. So it's negative 2,000 times sine squared of 0.5 times 0.01. Throw that in my calculator and I get a negative 87.0. This is meters per second, if I'm not mistaken, does it say? Yes, because it's in meters, so it's in meters per second. And so when I do this in my calculator, make sure your mode is in radians, because calculus is always done in radians. And this part here, recognize that this is a clue for part B.